So hello everyone, this is ADITYA MISHRA and we are here with our third lecture on aerodynamics, on lecture series specially meant for students, those who are willing to appear for GATE examination or planning to take aerospace or aerodynamic engineering in their higher educations, right? So in today's class actually we are going to talk about one of the first and foremost theoretical model which was an idea actually which was developed in order to explain the physical observation of behavior of air over a three-dimensional wing. So how this air behaves, air moves when a three-dimensional over a three-dimensional wing was first presented by a renowned scientist and his colleagues, that's called Ludwig Prandtl. Okay, so Ludwig Prandtl actually tried to come up with an idea or theoretical theory to explain how the flow why the flow behaves like what is observed over a three-dimensional wing. So first, let us clear about what is a three-dimensional wing. A three-dimensional wing is basically a real wing. In real life, we can have wing with wing tips. Okay, so that means the value of a wingspan will always remain constant, right? It will have a constant length from one tip to another tip. Okay, and this is actually called as a three-dimensional wing. Practically it is not possible to have an infinite wing, a wing which is never ending, which has not no tips actually, right? So infinite wing is basically a hypothetical or a simplified version to understand the behavior of flow over the wing of an aeroplane. So a finite wing is basically a wing with wing tips. When a wing has a wing tip, there is change in behavior of a fluid. The flow interacts along the corners and edges, and that's called a three-dimensional effect. So because of the finiteness of the wing, because of the tips of the wing which is visible to the air which is moving in the flight direction, the flow behavior actually changes. So to understand this, how the flow behavior changes, let's try to come back to Euler's equation, right? Over an aerofoil, we have seen that the upper surface is more curved compared to the lower surface. Relatively, the lower surface is flat. So to observe the continuity principle, the air has to travel faster on the upper surface and it has to travel slower on the lower surface because of the distance it has to travel. Now with increase in velocity, pressure decreases on the upper surface and pressure increases on the lower surface. This decrease in pressure and increase in pressure is compared to the atmospheric pressure. That means the pressure on the upper surface of the aerofoil is less compared to the atmospheric pressure, and pressure on the lower surface of the aerofoil is more compared to the atmospheric pressure. So this difference in pressure actually makes the aerofoil lift. Okay, from the two-dimensional concept of a wing. Then coming to three-dimensional wing, actually if we try to understand how the flow behaves because of the finiteness of the wing, let's consider 3 points. So this is point 1, point 2 and point 3. So if you could see, point A is on upper surface, point 1 a red color is on upper surface, this is lower surface, and this is neighborhood or on the atmospheric pressure. So because of the difference, the pressure on the upper surface is less compared to the atmospheric pressure. Okay, so pressure always, and air always moves, fluid always moves from a region of high pressure to a region of actually low pressure. So here this is low pressure, that is high pressure. The air will tend to move towards the root. From the tip, the air will tend to move towards the root of the wing, right, on the upper surface. And because the lower pressure, as you can see, pressure on the lower surface, because the pressure on the lower surface is more than the atmospheric pressure, the air will tend to move from high pressure at the bottom of the wing to the low pressure area in the neighborhood. This results actually in curling of the flow, right? This results in curling of the flow around the edges. On the lower surface, flow moves outward, and on the upper surface the flow moves inward. Okay, this curling of a flow is actually also assisted by the flight speed. okay, in the forward direction, because the air is continuously moving over the wing, the curling of the wing actually pushes the air on the upper surface to tend or to tilt towards the root of the wing, to this side. And on the lower surface, as you can see by dotted lines, the air is pushed to move in the outward direction. So all these actually inward and outward, from the upper surface the inward motion, and the from the bottom surface the outward motion towards the tip of the air. Okay, so these aerofoils these actually meet at the edges. Okay, both the air which is going inward and which is going outward, it results when both the air from the lower surface and upper surface, they meet at, so this is the leading edge, and that is the trailing edge of the wing. Leading edge and trailing edge. The air when leaves the trailing edge here at the bottom, from the upper side and lower side, the air is moving in different direction, which results in generation of a you can say a twist. Okay, the air gets curled when leaving the surface of the trailing edge of the aerofoil. So these there is a generation of a vortex. Okay, so there is generation of a vortex which combines together to form here this kind of a structure. Okay, over the entire surface, the curling motion of the flow results. These are called trailing edge vortices, and all these small tiny trailing edge vortices, they combine together to form a single vortex at the outer edge, right? So this outer edge vortex is known as wingtip vortices. Okay, so these vortices are very important when we talk about from the aerodynamic point of view, the difference of pressure on the upper surface, lower surface, plus the forward movement of the aeroplane results in the formation of these wingtip vortices. Wingtip vortices are actually formed by combining all the trailing edge vortices which are distributed over the surface. We don't have a picture here right now, otherwise I would have we will be able to see what actually are trailing edge vortices. Okay, but we can also refer internet, that's an easiest way. Then the curling of a flow results in the formation of actually it should be wingtip vortices. Okay, then the wingtip vortices, so when we talk about these wingtip vortices, these vortices which are produced here at the edges or tips of the wing can be divided into two components. So there are two components of velocity, as we can see. One will be flow velocity component, which is trying to move the flow in outward direction. So this we can call it as a lateral component. So there is outward lateral component, and one will be component will be in downward direction. So this wingtip vortices can be divided into or the flow can be divided into two components, one which is trying to take the flow outward, and one which is trying to take the flow in downward direction, right? Because of these lateral components, the aeroplane wing actually feels like, instead of air coming straight on the surface of aerofoil, the air is actually getting pulled in the downward direction, something like that. Okay, so we can see here, instead of air which is moving straight on the surface, straight to the surface of aerofoil, because of the presence of this downwards components to the aeroplane wing, it feels like the air is going down. So this is how actually a three-dimensional wing behaves. Okay, it is completely how the wing observes, how the wing sees the air, what does the wing feel, how the air is coming onto the surface of the aerofoil. So this is how a three-dimensional wing behaves. In order to explain this behavior of a three-dimensional wing, Ludwig Prandtl, he came up with a theory or an idea or a theoretical model. Okay, so Prandtl's lifting line theory is a theoretical model which is trying to explain the behavior, why the air behaves like it behaves on the surface of three-dimensional wing. So actually this theory attempts to predict the aerodynamic properties of a finite wing, a three-dimensional wing, a wing which is having wing tips. Then it is also helpful till today in preliminary basic basic calculations of lift, drag, and induced drag actually. Pressure coefficient, pressure, lift, and induced drag. So we'll try to see how what actually this this idea, what was this idea philosophy, what philosophy did Prandtl use, what concept did he came up with idea he came up with in order to come up with this theory, right? So Prandtl's lifting line philosophy, what actually he does is he actually replaced the wing. So as you can see here, the wing is center line of the wing is actually, will place this value as 0. Okay, so center line is at 0, and on the other edges the value of this y component is plus b by 2 and minus b by 2, right, over the wing. Okay, so what he did is Ludwig Prandtl actually replaced the finite wing by means of a set of bound vortex, okay, and two free trailing edge vortices. Okay, so one bound vortex and two free trailing edge vortices, when combined together, it forms a single horseshoe vortex because it looks somewhat like an horseshoe. That is actually called as a horseshoe vortex. So the entire, so Ludwig Prandtl and his colleagues actually came up with this idea. He replaced actually the theoretical model. In the theoretical model, this is pure theory actually. Okay, so the theoretical model actually replaces the entire wing by means of a single horseshoe vortex. This single horseshoe vortex comprises of one bound vortex and two free trailing edge vortices, right? So that is the philosophy of Prandtl's lifting line. But when the formula is used for investigations, it was found that the model, okay, the induced velocity, the component of induced velocity over this single horseshoe vortex produces an infinite value. Okay, so if from this equation we can see that if y becomes b by 2, the denominator will become 0. Okay, or if this becomes minus b by 2, the denominator is going to be 0, which will result in infinite values. So which is actually not correct. Practically it was observed that the values shouldn't be infinite at the tip vortices. So this is the formula for calculating the induced downwash velocity. So this is actually, we have seen the velocity which is pulling the air in the downward direction. The distribution of that velocity along the finite wing, along the span of the finite wing, is presented here in this particular figure. And the value for calculating this, the velocity at any point y, from starting from 0 to plus b by 2, or starting from 0 center line to minus b by 2, this value can be calculated from this expression. But because the theory actually had some drawbacks, it produces infinite values. Technically every vortex has an infinite value at the center, but however this was not able to predict the lift values actually observed or experimentally obtained. So what they did, Ludwig Prandtl, they found out that a single horseshoe model is not sufficient enough to reflect the practical observation, the laboratory experimental observations. So they decided to replace this single wing by means of a multiple horseshoe vortices. Okay, so they presented, now instead of representing a wing by means of a single horseshoe vortex, now they actually presented with many horseshoe vortices, which with the bound vortices, they are placed along a single line. This line is known as lifting line. So the name of the theory, Prandtl's lifting line theory, comes from here. The line over which the lift distribution or circulation is obtained, that line actually it is called a lifting line. So the name of the theory comes from this particular line. Also the value of induced downwash velocity can be calculated with this. So downward change in downwash velocity at for any small distance on this line will be equivalent, or it will be equal to the negative of rate of change of circulation and the distance of the point where we are actually interested in calculating the downwash velocity. Fine. Now, so in order to have this, actually this is here, it is an intermittent value, so step by step increase, which can be clearly observed here. Okay, to have a continuous distribution, okay, with a continuous increase, that means definitely using this theory, the lift will be lift generated by the wing will be maximum at the center line. Okay, but the distribution, to have a continuous lift distribution from the tips to the center line of the wing, it has to be superimposed by means of multiple infinite horseshoe vortices. So every horseshoe vortices can be observed here. This is one of the biggest horseshoe vortex, and then we can have a small tiny vortex. So every horseshoe vortex superimposed here they have a different length of bound vortex. So for first one, this is the length of the bound vortex. For the second one, the length of the bound vortex actually decreases, and for the third one again can be observed from here to over there. So all the bound vortexes, they are superimposed, and where they are combined together, this line along the y-axis is known as a lifting line. Okay, and for the total overall distribution, we can use this formula for calculating downwash over the entire circuit. In the coming classes, actually we will talk about the calculation, how the lift, drag and pressure coefficients are calculated for using lifting line theory. Thank you very much, and I hope this is helpful to all of you.